Hi, my name is John Krockmalling, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll explore wattage, what it is, and how it relates to electrical physics. We will also review how wattage is used in electrical circuits. There will be three learning outcomes associated with this presentation. Number one, describe electrical watts. Number two, relate electrical watts to load power. And number three, describe electrical purchase components. When we think of the power available to operate a water power mill, we may believe that water flow is necessary to move the paddle wheel. Any flow of water will be determined by a pressure difference between 2 points in that water circuit. As we may already understand, there needs to be a pressure difference in anything for matter to flow or move. If work is going to be accomplished, we can take into consideration how much force in pressure was applied and how much of a resultant movement was accomplished. Mathematically, power is determined by how much pressure in pounds was applied multiplied by the movement of matter over a distance of feet, and that product is divided by the amount of time in seconds this movement happened within. In this graphic, we can identify the effect of pressure difference has on flow. The higher the pressure difference, the greater the flow rate. Going back to our paddle wheel, greater power is given to the paddle wheel and can be accomplished by increasing pressure and/or increasing the flow rates. It's a similar pattern to electrical circuits. The term watts is the electrical term for the power used by an electrical load. To calculate wattage, the voltage pressure is multiplied by the amperage flow. Notice in this example, the value of the voltage pressure is multiplied by the value of the amperage flow to give us a wattage of 120. This 120 watts is the power used by the electrical load. In this graphic, we see an applied 240 volts of electrical pressure and the resultant flow of 4.8 amps. In this example, the calculated power is 1152 watts and is determined by the voltage multiplied by the amperage. 120 volts of electrical pressure applied to a load, resulting in an amperage of 4.8, results in an 1152 watts of power consumed by the load. If watts is the measurement of electrical power, the greater the value in watts, the greater the electrical power consumed by the load. We may all realize that a 75-watt light bulb is brighter than a 40-watt light bulb. They both are supplied with 120 volts of electrical pressure, but their amperages will be different, resulting in the wattage difference. In this case, the 75-watt light bulb, the brighter one, uses 0.625 amps. The 40-watt light bulb, the dimmer one, will use 0.30 amps. The higher the watts, the more power is used. When it comes to electric motors, we have a load that converts electrical energy to rotational mechanical torque. When considering motors, the power rating of horsepower is used. 1 horsepower is equal to 745.7 watts. In this graphic, we can see that 1/4 horsepower motor is less powerful than the 3/4 horsepower motor. Notice that the 1/4 horsepower motor develops approximately 187 watts, and the 3/4 horsepower motor develops approximately 562 watts. Transformers convert AC voltage to AC voltage and are sized according to their VA, or volts times amps power. In this graphic, we see the transformer sized for 20 VA. On the secondary side of the transformer, 24 volts are present, along with a maximum amperage of 0.833 amps. Electrical power is purchased from the electrical utility that generates it. This purchase not only includes the watts used, but also the time spent in using that power. Going back to our light bulb, we may be using 75 watts of power to turn it on, and that the light bulb is illuminated for a definite period of time. If we include this power with other electrical appliances that we might use throughout the day, we can total the consumed power from the electric utility. For example, we may use a total of 14,733 watt hours per day using various appliances. Utility companies use kilowatts or watt values in thousands, making electrical meter reading easier to read and bill. The billable power then becomes 14.73 kilowatt hours or kWh per day. Multiplied by 30 days in 1 month, we see a total of 442 kilowatt hours, and it appears on the monthly utility bill. If the electric utility company bill charge is 20 cents per kilowatt hour, we see a monthly bill of $88.40. This is the price that is paid for the electrical power provided to us by the utility company. We already understand that electrical wattage is found if we multiply voltage times the amperage. There are two other methods to determine wattage. In Formula 2, wattage is found by taking the amperage, squaring that value, and then multiplying it by the value of the resistance in ohms. In Formula 3, wattage is found by taking the voltage, squaring that value, and then dividing it by the value of the resistance in ohms. Let's use this ladder diagram located on the left to determine the circuit wattage using the three power formulas. Referring to equation number 1, we multiply the 240 volts by the amperage of 4.8 to arrive at 1152 watts. By applying the second wattage formula, we find that by squaring the 4.8 amps, we get 23.04 amps. And then by multiplying this product times 50 ohms, we get 1152 watts. In the third equation, when we square the 240 volts, we get 57,600 volts. Dividing this by 50 ohms of resistance, we also get 1152 watts. Remember, the equivalent of electrical power is termed watts. The wattage is the power consumed by the electrical load in the circuit. It is the wattage that is provided by the source of the electric utility company. When considering that this is purchased from the utility company, the billing of this power will be in kilowatts.